now we are going to prove the other one is a mixed strategy Nash, which is this one. The first player mixes between two of his actions, and the second player only chooses R. So there's nothing to solve here because this is with probability 1, and this happens with any probability. We'll see it like this. So if the other guy plays R, then no matter what combination I choose, I always get 1, so it doesn't matter. So basically, alpha can be anything. So the only thing we need to do is we need to check condition 2, or the support condition, which it says playing R, playing what I have in equilibrium must be better than playing the thing that I'm not playing, which is anything in this form. No, that's not right. This is C here. So if I play R, then I get payoff 1 as before. If I play L and C, then I would get 2 with probability alpha times beta, which means I get 2 only if the first guy plays U and I'm playing L. So it's 2 times alpha beta, and plus another 2, which is here, times 1 minus alpha, 1 minus beta. So that would be the expected payoff that I get if I'm using this mixed strategy and fixing the other guy's strategy. So this must be true for all beta. So R basically needs to be better than any mix that I have, and alpha doesn't really matter, so we can fix an alpha. Then we probably need to simplify this a bit. So 4 times alpha beta minus 2 alpha minus 2 beta plus 2. So since we are doing it for all beta, so we probably want to maximize this thing with respect to beta, so we will factor it in a way such that it works. So maybe 4 times beta alpha minus a half minus this plus 2. So know that we need this to be true for all beta, but if the beta that maximizes this expression works, then for all other beta, this will be smaller, so it will be even better. So the way that we are going to solve this is, if it works for the beta that maximizes this expression, then it will work for all beta. So we will find the beta that maximizes this expression. So you can see that it's linear in beta, so whatever the coefficient, if the coefficient is negative, then the optimal beta would be equal to 0, because this is negative, so I want it to be, beta wants to be as small as possible. Then the condition becomes, this implies condition 2. Substituting beta equal to 0 here is 1 to be larger than or equal to minus this plus 2. So if we rearrange this a bit, it's alpha larger than or equal to a half, which then there's a contradiction, right? So we assumed alpha to be smaller than a half to begin with, and we concluded that alpha must be larger than or equal to a half, so that there is a contradiction. Then we do the same thing with the other side. So if alpha is larger than a half, let's go through this again. So this number is positive, so if we want to maximize this whole expression, beta needs to be as large as possible. So we have 1, so this implies condition 2 will be 1 being larger than, substitute this equal to 1, becomes 4 times alpha minus 2 alpha plus 2. So it becomes 1 is larger than or equal to 2 alpha, so alpha is smaller or equal to a half. So again, this doesn't work, because there is contradiction. So actually alpha cannot be anything other than a half. So let's check whether this works actually. So if alpha is a half, then no matter what happens, so any beta, it doesn't really matter, because this total will be 0 anyway. So the second condition becomes 1 is larger than or equal to just this. And here alpha is equal to a half, so let's replace this by a half, and this is 1, yes, which holds. So then from this case, we can conclude that the only mix strategy is not any mixing. So at the beginning, we said any mixing is okay. Now from this analysis, we see that it's not actually right. So we only have this.